Let us start today's class, single phase AC circuits. In that, I was discussing about AC through pure capacitance. We have completed previous class AC through pure resistance, AC through pure inductor, and the corresponding derivations. Now let us talk about AC through pure capacitance. Consider a simple circuit consisting of a pure capacitor of C farads connected across a voltage given by the equation V is equal to Vm sin omega t. The circuit is shown. The current I charges the capacitor C, the instantaneous charge Q on the plates of the capacitors. Q is equal to Cv, current I, rate of flow of charge, I is equal to dq by dt. When we write that here, finally we land up with the equation Im is equal to Vm by Xc, X is equal to 1 by omega C. The above equation clearly shows that the current is purely sinusoidal and having a phase angle of 5 by 2 radians, or you can look at the diagram. Here, this is about resistance. This is here, you can see the relation having the phase angle. There is a the current is purely sinusoidal and having phase angle 90 degree. This means current leads the voltage by 90 degree. The positive sign indicates the nature of current. Here, the concept of capacitive reactance, the term Xc is 1 by omega C or 1 by 2 pi Fc. We call it as capacitive reactance and is measured in ohms. The capacitive reactance is defined as the opposition offered by the capacitor of a circuit. You can see there to the flow of an alternating sinusoidal current. Xc is measured in ohms and it depends on the frequency of the applied voltage. The total power consumed by this will be zero. The expression for the instantaneous power in case of pure capacitance is given here. It can be obtained by taking the product of instantaneous voltage and current. P is equal to V into I. Then we land up with the final relation. P is equal to Vm by root 2 Im by root 2 into sin omega 2 omega t. Rp is equal to 0 when you integrate it for one cycle. Thus, power curve is a sine wave of frequency double that of applied voltage. The average value of sine curve over a complete cycle is always 0. We can see, you already observed that in the diagram. It can be observed from the figure that when power curve is positive, I'll show you the diagram. When power curve is positive, look at the diagram. See here, you can observe that when power curve is positive, in practice, an electrostatic energy gets stored in the capacitor during its charging, while the negative power curve represents the energy stored is returned back to the supply during its discharging. The areas of positive and negative loops are exactly the same and hence average power consumption is 0. That is pure capacitance never consumes power. The average energy stored in a capacitor is always given by half CV square. Keep this in your mind. So this completes today's class, AC through pure